Okay, on to video number 3. We've talked about the systems, how the systems regulate. We talked about distribution of fluids around the body. Now we're going to actually talk about some fluid or regulation imbalances. So you definitely have to remember your concentration terms, and I don't know how I found this with the other language. I don't even know what language that is. It looks like maybe German. But what's interesting is you have to remember the different concentration changes and what's going on. So if I were to ask you real quick, what is isotonic in the body? So if I asked you about like a saline solution, what's an isotonic saline solution? It's what percent sodium? So it's 0.9% sodium chloride. If I asked you, it's milliosmoles. So if I asked you that question, how many milliosmoles are there? There are 300 per liter. So those are the terms to remember for isotonic. If it becomes hypertonic, what happens to both of those numbers? They go up. So 300 milliosmol will go up to like 700, 1,200 if you're looking at the kidney. Huge range. That's hypertonic. If you're talking about a salt solution, like saline solutions, and you said hypertonic, you can think if it goes from 0.9% up to, like, say, 1.5, which doesn't seem like much, but that's a huge difference. That's a very salty solution. What would that solution do to your cells? It would make them shrivel up. So definitely remember those terms. Remember what isotonic is. It's 300 milliosmolar or 0.9% saline solution. All right, so when you have isotonic alterations, or a change in volume or a change in fluids that's isotonic, you have to remember that the total body weight changes proportional to the electrolyte and the water change. So if you are urinating too much out, you're actually going through a process called diuresis, and it's called osmotic diuresis because the percent of concentrate, like solutes to solvent in your urine, is exactly the same as normal urine. So you're urinating lots of fluid out, lots of electrolytes out at the same time. So that's isotonic. Your blood volume would drop. What would happen to the tonicity of your blood? Nothing. It would still be isotonic. It would just drop. So when you're looking at isotonic fluid changes, you can have a fluid loss or fluid excess. So isotonic fluid loss, lots of causes. I actually just mentioned one. So diuretics. If it's pushing out electrolytes with water, it's an isotonic fluid loss. You become dehydrated as a result. You could have a hemorrhage, so bleeding. You're losing blood, isotonic blood, so it goes out and leaves you with less volume, but it's isotonic volume. So those are just a couple examples. So once you know the cause, you can kind of predict the signs. If you're losing volume, what's happening? Your blood volume's going down. So you're going to lose weight because every time you lose a liter of fluid, you lose a kilogram of weight. You might see dry skin because the fluid's not being distributed properly, so the skin starts drying out. Mucous membranes, mouth starts becoming really dry. Decreased urine output. Why would they stop putting out urine? Unless, of course, it was when they're in a diuretic state and the kidney's broken. They stop putting out urine because they're trying to retain salt and water. They're trying to retain both in isotonic solution. And then they get hypovolemia. So, of course, with hypovolemia, you have to worry about pressure dropping, so shock. So why would this cause a rapid heart rate? If you decrease your volume, why is your heart beat faster? You see that symptom because it's trying to push blood it's trying to push the same amount of blood to the tissues all the time. If you don't have very much volume, you have to increase the rate. So having a faster heart rate, hyper heart rate, dry mucous membranes, decreased urine output might be a sign that you're becoming dehydrated. And then, of course, most extreme, you have to worry about drop in blood pressure at the point of shock. Some other signs you might see: flattened veins. Why would they be flattened? Because they're lacking volume. Just the opposite of isotonic fluid loss, isotonic fluid excess. It's really hard to actually have this. Typically, this is iatrogenic. And if you remember that word iatrogenic, iatrogenic, it means who did it? The doctor or medical provider. So it could be the doctor, it could be a nurse. It's just somebody that's giving them medical treatment is doing it. And iatrogenic here would be excess IV fluids, so putting too many IV fluids into them. So it's isotonic fluids, they're pumping in too much. Another problem might be for isotonic fluid excess is if they have something like too much hormone. So if they're releasing too much aldosterone and cortisol, then they're going to retain lots of salt and lots of water. Cortisol, by the way, I know you know cortisol is the stress hormone, but cortisol also acts like an antidiuretic hormone. It helps you retain water. So, and when you think about it, it makes sense. In high stress situations, you want to get your blood pressure up to get more blood to the brain, cortisol is going to do everything it can to increase your blood pressure. And in physiology, you probably learned it increases your blood sugars, your blood fats, your blood proteins for energy, increases your blood pressure by causing vasoconstriction, but now you can remember it as retaining water too. So if you have like a tumor on the adrenal gland that's releasing too much aldosterone, that too much aldosterone makes you retain salt. Too much cortisol makes you retain water, causing isotonic fluid excess. Right? This usually leads to things like edema. So here you had hypovolume, here you have too much volume, and that volume starts leaking out. So I put these little giraffe balloons in here as an example, but in somebody with isotonic fluid loss, you would see signs of like low pressure, flattened neck veins. Here, with fluid excess, you're going to see lots of leakiness. So they're going to have high blood pressure, they're going to have edema because all this extra fluid is leaking out and going into the tissues. Right? They might actually lead to heart failure. So too much fluid, too much pressure, the heart's pumping too hard, and it might just actually stop. So those are some of the signs and symptoms you might want to look for. Right, so how do you get hypertonic alterations? In other words, if it's hypertonic, what could be happening? One of two things. Right? Your total body weight can change, but it's not proportional electrolytes to water at the same time. It's actually disproportional. So you're losing way too much of one, or you're gaining way too much of the other. So if it's hypertonic, the solution is gaining what? It's gaining the solute. It's gaining the sodium or the sugar or proteins. It's gaining some kind of a solute. It's becoming too hypertonic. What's going to happen to the cells in a situation like that? So here you have a hypertonic solution going through your blood vessels. Remember, these solutes are like little water magnets. They're pulling the water into the blood. So if they're pulling it from the interstitial fluid, this decreases. Where's the interstitial fluid going to get makeup fluid from? It pulls it from the cell. What's happening to your cells when your blood is hypertonic? Cells shrink. Right? So here, you're pulling the water into the blood. What's happening to the blood volume? It's hypervolemic. So you get hypervolemic symptoms. What's going to happen to your blood pressure as a result? It's going to go up. Yeah. So because of the shift of fluid into your blood, it makes your blood pressure go up. If it's because you did something like you ate way too many pretzels, you took in lots of pretzels, and now you're pulling all that water into your blood and your blood pressure is rising, what organ's going to have to try and fix that? So your GI tract just caused the problem by absorbing too much salt. You have to think of what organs are going to compensate. Well, you can think the nervous system's probably going to do what to the sympathetic nervous system? Turn it down. Yep, it's going to turn it down to decrease the blood pressure, which is going to increase flow to the kidney, right? So what's the kidney going to do? If you have too much salt in your blood, the kidney's going to stop releasing renin, and it's going to help you excrete the salt. So the salt's going to slide right into your urine and get rid of it. What else would the nervous system do? Would it release more antidiuretic in a hypertonic solution? So in a hypertonic solution, yeah, it releases antidiuretic, which is going to help you retain water, right? It's going to bring the water in to try and dilute that solute. So you have to think more than one step. It's not an absolute. Like if you release antidiuretic, you have to release aldosterone or vice versa. So you shut off the aldosterone to get rid of the salt, but you release antidiuretic hormone to try and retain water. You're trying to dilute the salt back down so you have an isotonic blood again. Always think a little bit in advance, and don't try and think everything all at once and memorize everything. Think one step at a time. What happens if you retain salt? Well, you know that it's going to make your blood hypertonic. If it makes your blood hypertonic, how can you fix that? You try and get rid of the salt and add water. And then you think of the organs that do that for you. The other problem that could possibly happen is that you have too little solvent. So too little, what's the universal solvent? Water. What could you do to have too little water? Usually it's one of two common causes. Either you're urinating too much water out, you're pushing out way too much water, and in that situation, because it's a hypertonic situation, you're pushing out pure water or close to pure water. So you have water diuresis. You're peeing a lot and it's lots of water. Usually it's going to be really clear. Right? Or you're not taking in water. Your input is less than your output, in other words, for either of those situations. So those are typical causes. So some of the signs, tachycardia, weak pulses, postural hypotension, right? You're not getting enough water in your body. So in this situation, you have too much salt, which is going to raise your blood volume and blood pressure. Here you have too little, so they're just the opposites. So tachycardia means fast heart rate. Why do you have fast heart rate if you have low blood volume, low water in your blood? Because it's trying to push it faster and distribute it more evenly. Right? Here's some interesting things. You're going to have an elevated hematocrit. Hematocrit, remember, is measuring your red blood cells. Does that mean that in the situation when you don't drink water, you make more red blood cells? That seems weird. It is weird. You're not making more red blood cells. You have to think. If you decrease the water amount in a liter, what's it look like everything else is doing? It looks like everything else is increasing. So what you're happening here is you're dehydrated. They call it relative polycythemia, which means that you're not making more red blood cells. You technically don't have too many in number red blood cell. It means that you have too little water, which means you have less plasma. So think about these pathways. Right? What's going to happen to your heart if it looks like if there's proportionately more solutes, in other words, more platelets, more proteins, more red blood cells, more salts? What's happening to your blood? It's becoming very watery or thick? It's becoming thick. What's happening to your heart as a result? You have to pump harder to move that syrupy blood. Right? So they get issues with the heart, tachycardia. It's pushing harder, it's pushing faster, it's trying to get more blood distributed. They become hypovolemic because they don't have enough blood or enough volume in their blood. Right? And then think, how would you compensate? What would the kidney do to compensate for this? The kidney would probably start retaining more water. Yeah, it'd start retaining more water to try and bring your blood volume up, to bring your blood pressure back up to the way it should be. What might your brain do? What might your hypothalamus do? Well, if you have too little water, your hypothalamus is going to make you want to drink more, thirsty, and it's also going to make you want to do what with ADH? Turn it up or turn it down? It'll make you want to turn up the antidiuretic so you retain more water. And the next slide actually goes through an example. So in a quick fix, here's kind of a pathway your body might start taking in. So let's say your total body sodium went up. It doesn't mean that you absorbed more sodium. It could be that you lost water. Either way, it looks at, through osmoreceptors, it looks at how much sodium's there. The hypothalamus is going to start making you want to drink water. It makes you thirsty. You can also think it's going to release what? It might release some ADH. Right? So your total body sodium went up. It's going to release ADH to help you retain it. More water to dilute that. Right? In the process, while you're drinking water, you have an osmotic shift. The water starts getting pulled out of the cells. Too much salt, hypertonic solution. The water is being sucked out of your tissues. It's raising your plasma volume. So now your plasma volume is going up. Now you have this atrial stretching. The atrial endocrine cells, remember the cells in the heart that release that stuff called ANP or ANH. So atrial natriuretic's the key here. Are going to make you start losing salt. What turned on this pathway in the first place? Too much salt. So now you're going to start losing salt. You're gaining water, you're losing salt. You're trying to bring everything back to homeostasis and balance. Right? So ANH, ANP, goes down to the tubules, and it causes you to decrease reabsorption. You're going to stop reabsorbing salt. In other words, you're going to urinate salt out. Okay? You're going to stop releasing renin, because remember, renin is going to turn on aldosterone eventually, make you retain salt. So you stop that. Right? By the way, your blood pressure's changing a little bit. It's going up, plasma volume, so that's going to stop renin from release too. And then AMP is going to go to the glomerulus, and it's going to try and increase glomerular filtration rate, which means it's going to try and push more fluids through the glomerulus. What's it trying to do? It's trying to put more salt into your kidney. And when it puts more salt in the kidney, come back here. It's going to try and excrete it. So overall, you've got several chemicals in a pathway that you have to be familiar with how they all work together. And then the last of the three is going to be hypotonic alterations. So in this situation, you have two possible pathways. You can have too much water, or you can have too little salt. Right? So too much water, what could possibly cause too much water? Bringing too much water in. You're bringing way too much water in. So it's like compulsive water drinking. You're just drinking a ton of water. If you're drinking water, we're not talking Gatorade, we're talking pure water. Are you bringing more electrolytes in? No. So you're diluting your blood. Right? Now that blood is hypotonic. Remember what happens to cells in a hypotonic solution. The water goes from the blood out to the interstitial. Here we go. So too much water here, high proportion of water here goes into the interstitial space, and from the interstitial space it goes into the cells and makes the cells swell. Well, what happens if this is brain? So water goes into the interstitial space and into the neurons and causes them to swell. That's known as cerebral edema. Is that dangerous? yeah, it's life-threatening. It could actually kill you. So you don't want swelling at the brain. It's going to do water shift into the muscle too. So the water starts shifting across into the muscle to hold the water and causes twitchiness. You get headaches, you get weight gain, you're holding too much fluid. Right? What's going to happen to your urine concentration? Right? So if you have way too much water, what should start happening? What's your urine going to do to compensate? You're going to try and push more urine out, right? So you're pushing out way, way, way more urine. What's that urine going to look like if you have too much pure water? It's going to look like pure water, right? So it's going to look very clear. Why would this cause hypervolemic symptoms? So too much solvent. Why would it cause hypervolume? You have way too much water, too much volume, and then if you want, you can look back at the hypervolemic symptoms. So high blood pressure. Too little solute, exactly the opposite. So it's still hypotonic, but you've lost salt for what reason? So what's one possible thing that could have happened? What hormone could have been released that's going to cause you to lose too much salt? It could be ANH that we talked about in the last couple slides. So ANH, ANP, atrial peptide or hormone, is coming out and you're losing way too much salt. Okay? What hormone might not be working? What hormone may not work that normally keeps you retaining salt? Aldosterone. So maybe there's something wrong with the adrenal gland. It's not releasing aldosterone. If it's not releasing aldosterone, you can't retain salt, which means you lose too much salt. Right? So when you look at the measurements, and I put C, the particular solute, because in the next video we're going to talk about specific solutes like sodium. But it doesn't have to be sodium all the time. It could be other things. It could be like sugars. Right? But when you take a measurements, they're going to have low serum solute of whatever that is. Okay? They have hypovolemic symptoms because they're starting to urinate things off. They're trying to clear away the water, so the water volume is going to start dropping. But it's not because of the water, it's because of the solute. They're trying to get rid of water over here so that they bring the proportion of solute back up. So when you look at these symptoms, usually they're almost always the opposite. When you look at the causes, they're the opposite. When you look at the solutions, they're the opposite. So both are hypotonic, but you have to look at what's changing. In this situation, it was the water. In this situation, it was because of this solute. So the next question, and this is kind of an interesting one. For years I've been trying to figure this out, or I keep trying to remember to go do it, and now I'm having you do it too. So I want you to do a web search, and you're going to look up Jennifer, Strange, and we. So these three words, you can put Jennifer plus Strange plus we, and that way you make sure all three of these pop up in the same article. This time I'm not looking for a .gov or a .org or whatever. I'm looking for whatever you can find out about this situation, but look for some kind of a reputable source like a television news website or a reputable newspaper website or something like that. Right? So here's what I want you to write down. Google that, and I want you to write down what was the name of the cause of her death. So what was the disorder that they said she died from? Okay? What was she doing when she died? And here's where you're going to do the interpretation, because journalists are probably not going to do this for you, but you're going to say what the pathogenesis is. So what solute or solvent, oops, that's a typo, what solute or solvent was primarily affected in this situation? Right, so was it the solvent or the solute that made the biggest impact? What was the cause? What happened to her cells? So because of the change in the solvent or solute, what happened to her cells? And then how would the organ beside the kidney try to compensate for this? Right? Because she was doing something where she was actually not using her kidneys, so other organs had to try and compensate. So in other words, what signs would she have given as indicators that she was in trouble? So go ahead and pause, write that down, and do the Google search. It's kind of an interesting article too, and you've just learned about another disorder. All right, the last section in this area is edema, and we're going to talk about 4 common causes of edema, and then actually we'll be done. So edema, first, what is it? It's accumulation of fluid in the interstitial space, so between the cells. Some people say that you can get edema in the cells, but it's not technically edema. So we're going to look and focus at the interstitial spaces. Up here is an example of pitting edema, where you can squeeze down on somebody's foot, pull your finger away, and it leaves that indentation. And it's a sign that this is lots of fluid in here. When you squeeze down, you push the fluid to other areas or down into the blood vessels. But that's kind of the idea behind compression stockings, is that it squeezes the tissue and keeps the fluid in the blood instead of in the tissue. Right? There are other types of edema. You might see edema down in the abdominal area. You might see it around the lungs, and we'll talk about some of those signs. You might see it like like a vein being blocked up and all the pressure's pushing fluid into the foot, but the vein's not allowing it to leave, so you get swelling in that area. Right, so clinical signs, swelling, puffiness, localized to wherever the site of trauma is typically. You can have systemic edema where the whole body is actually swelling, right, which we'll talk about a little bit. And of course, when it's systemic, when they stand all day, why do they get this pitting edema at their feet? Because of gravity. Gravity's pulling it down, so the swelling's here. And then those people lay down at night, they go to sleep, they wake up the next morning and no swelling. Did that mean the edema went away? No, it just means that the edema spread out more across their body. It's more distributed, and then they're on their feet for another hour or two, and the swelling comes back in their feet. Some of the problems, they have slower chemical reactions in the cells, which means they heal slower. The infections don't go away as fast. And depending on the organs, if it's specific organs like the brain, the lungs, it could actually be life-threatening. We'll talk about that. So, how to treat. And if you know what causes it, you just reverse that cause, and that's the treatment. Right. I really want you to remember these hydrostatic pressures, or hydrostatic and osmotic pressures. So go back and look at Starling's hypothesis again if you need. But any change of these four things can cause edema. So how can you change each force to cause edema? So in other words, your blood pressure, what could happen to your blood pressure that would cause it to push more water out of the blood vessels and into the tissues? Well, blood pressure could go up. Higher blood pressure can cause the edema. It's pushing more force into your tissues, and evolutionarily, this is a good thing because it's trying to get circulation of those tissues, but when it's excessive, it causes them to puff up and swell. So pushing the fluid from here and into the tissue can cause edema. Interstitial osmotic or oncotic pressure, water pulling, could go down. So hydrostatic pressure going up pushes more out, but if these tissues out here get loose, the collagen's weak, they don't support very well, they can't push the water back into the blood, so they just start puffing out and swelling. Okay, the reabsorption forces, so the first one, plasma oncotic pressure, the proteins in here. If you lose the proteins, water doesn't want to stay here. Water will leave the blood. So what organ makes the bulk of proteins? Hope you remember this from anatomy or physiology. The liver. The liver makes proteins, puts them here, and the proteins are little water magnets that reabsorb water, that pull water back in. But if there are no protein magnets, then suddenly the water seeps out and causes swelling. Right? So people with liver failure you might want to think of. They're not making those proteins, so they get swelling all over the place. And then interstitial hydrostatic pressure. So interstitial hydrostatic, I actually kind of talked already about. How did I miss that one? But the water pressure that's trying to push back in for reabsorption, if the tissues get weak on the outside, it can't push back in. Oh, I see where I made my mistake. Sorry. If proteins start seeping out here, so go back to filtration. So interstitial osmotic or oncotic, if proteins seep out here, they pull water out. So if you have more proteins that are in the tissue here, they pull more water. So I'll run through those again. Sorry about the mistake. Hydrostatic pressure, blood pressure going in here and pushing outwards. If you increase hydrostatic pressure, it pushes more water out. If you have more protein in the interstitial fluid, it pulls the water out here too. You'll see that when you have infections. So histamine opens the pores and lets proteins come out, and it pulls water with it, causing swelling. Reabsorption forces, so plasma proteins pulling back in. If you don't have the plasma proteins pull back in, the water seeps out. And the last one, interstitial hydrostatic pressure. If the interstitial fluid starts accumulating because the tissues aren't strong enough to squeeze the blood back in, they puff out. Right? So here are the four major causes one at a time. So hydrostatic pressure increases can cause it. In other words, if you have some kind of a blockage to a vein, the arteries, the arterioles are still pumping. They're pushing fluid down into that tissue, but if the veins get blocked, then the fluid starts building up in the veins downstream here. So let's say I have a blockage. I'm going to say I have a block right here. Right? So the arteries, high pressure, pushing fluid down here, but now the fluid's trying to come back up. The fluid can't get back beyond this, so it starts distending these veins. And those veins become inflamed. They start bulging out. And that if they're at the surface, you can actually see them. And you can see the pathway of the veins that are blocked here. Right? Varicose veins are another example. If you keep crossing your legs and you block these veins, that fluid pressure starts building up in your lower legs and can cause damage to these veins, and then they become visible because they're out at the surface. Another issue is that if you just have too much salt or water retention. If you're building up too many fluids, sometimes the fluids can't come back efficiently. The veins can only do so much. And if those veins can't carry the blood back efficiently, they start accumulating in the tissues. So congestive heart failure and renal failure are the two common causes of salt and water retention. So, and I'm sure you could probably automatically think about the kidney and how it contributes to retaining salt or water, but think about the heart. In fact, think about it for a point. So, homework question number 5. Can you tell me how congestive heart failure causes salt retention? Think about the hormones involved. Think about the blood pressure. Right? So, what happens to the pressure? If you have congestive heart failure, what's going to happen to the flow into the kidney? What change would that make on salt? And then how does renal failure cause salt retention? So you can look it up in the book, you can look it up from the slides because I talked about it a little bit earlier, or you can even Google it if you want. But just these two things. How does the kidney and the heart cause salt and water retention? Pause, write it down, and then we'll go on to the next one. Okay, next. So what causes decreased osmotic pressure? So the plasma osmotic pressure, remember, is because of proteins flowing through the blood. When proteins are floating through the blood, they pull water back into the blood. They cause reabsorption. So one problem is that you can have decreased plasma albumin. What organ did I tell you makes the albumin? The liver. So if there's a problem with the liver, then you're not going to be able to produce, or you're not going to be able to release the proteins into the blood, which means the blood won't be able to hold water. So a couple causes could do that. Maybe you don't have the raw materials. What builds proteins? Amino acids. So maybe you have protein malnutrition. Maybe you're not getting any amino acids in, and you can't make those albumins for the blood to retain water. Right? So with little children, I remember growing up seeing the ads on TV for starving children in different countries, and they always had this big belly. And it's because their belly's actually inflamed, which we talked about last week. But another thing is if you look at their feet are huge. They look like little cantaloupes with grapes on the end of them. They're so swollen and puffed out. And it's because they're not getting enough amino acids, which means they don't make albumin, which means fluids don't stay in their blood very well and they seep out in the tissues. Why their feet? Why do you see swelling at the feet? Not in the arms. You'll actually see it in their hands too, by the way. It's because of gravity. They don't have enough plasma proteins to pull water back in, so the water moves to the tissues and then gravity slowly pulls it down to their feet. And then another problem would be plasma protein loss, and there are a couple different losses. One could be that you have kidney failure or kidney damage. If the kidney is damaged at the nephron, normally do proteins cross? Do proteins come in here and go out to the urine? No, but if you damage the glomerulus, proteins could seep through. What's going to chase proteins? Water. So you lose water and it goes out into the tissues. Okay? So protein loss from the blood means that you can't keep water in the blood. And it starts seeping to the tissues. It'll start seeping to the urine. It's seeping all over the place. And then, I don't know if you know who this character is, but a protein loss can actually be caused by burns. So when you burn, you actually lose proteins. Proteins coagulate. And when you're coagulating those proteins, they don't stay in the blood, which means you lose water too. And that's why when you see burns or cuts or seeping wounds, all those proteins are going into the wound and they're pulling water into the wound at the same time. Right? Next cause, increased capillary permeability. Somewhere right in here, I want you to write down the word histamine. Histamine is the key player. So increased capillary permeability is primarily because of histamine. You get some kind of infective agent, histamine comes along, and the histamine opens up the pores in the capillaries. Normally, protein can't slide through these pores, but when histamine opens them up, protein starts seeping through. Well, when protein seeps through, what was to chase the protein solute? Water. Water seeps through. Water leaves the blood, goes into the tissue, and causes inflammation or puffiness. So here's an example. This person with an allergy, histamine was released all over her face, wherever this allergen made contact. It let proteins go into the tissue, and now water chases after. It's just a normal immune response. And then the last cause, obstructions. So lymph obstructions, not venous. We talked about in number 1, lymph obstruction. Because remember, when blood's being pushed along, it loses fluid into the tissues, but it doesn't collect all of it back into the veins. It collects most in the veins. So the leftover fluids go into the lymphatics. They get carried back through the lymph system, all the way back up, and dumped in the vena cava, right outside the heart. Right? So the lymphatics carry extras. Well, if you block up the lymphatic, you can't get adequate flow through the lymphatics. Now that water's going to accumulate here and puff up. Right? Like lymphedema. It's talking about the lymphs being blocked, and you get edema as a result. In this situation, they call it elephantitis. This guy has a parasite. The parasite came into his foot, went into his lymphatics. It's easier for the parasite to go in the lymph than the blood because it's low pressure in the lymphatics, high pressure in the blood. So it gets in the lymph, comes cruising along, goes up to the first lymph node and says, hey, this looks perfect for a home, and it builds a nest. So it moves up into his ankle into the lymph nodes, builds a nest. Now the fluid's starting to accumulate in his foot. Can't take care of it. Doesn't do anything about it. They don't have the medicine to get rid of the parasite. So the parasite makes babies and sends it to the next lymph node. Starts swelling in his lower leg. Sends it to the next next lymph node. Starts swelling around his knee. In the meantime, you still have accumulated fluid up to here. And then it goes up to the genital region, causes fluids to back up. Yeah, and yes, these are his testicles. The fluid's going into the testicles, but not leaving appropriately through the lymphatics. So it swells up. And you can see it's up in his arms and everywhere too. So it slowly moves up their body. It's a parasite. So in the United States, we take a medication that kills the parasite and it goes away. If it gets this bad, though, they just have to completely remove the lymph node. And once you remove the lymph node, it doesn't grow back. So they still have the problem. They just don't have the parasite anymore. Right? So they may wear some kind of a support stocking that squeezes the tissue and tries to push the fluid back into the blood. So there's a flow chart in your book that actually shows all these different things. You can look at any of the causes and how they lead to edema through the pathophysiology. Like increased capillary permeability means that the plasma proteins leak out, which means the fluid leaks out, causing edema. Right? So there are lots of examples. And then the outcome of edema. So here are some of the possible problems that happen. One is, it impairs the blood flow. So the bad thing is that if you have impaired blood flow, anytime you get a sore or a wound, it's going to cause slower healing. It's going to increase the risk of infection. And usually over bony areas that have the most pressure where you're compressing it are where you're going to see most of the damage. Right? You can have edema-specific organs. So in this situation, here you can see edema in the brain. It's causing depression in the brain, can cause problems, psychological problems, physiological problems. Life-threatening areas would be the brain, the throat, and the lungs for obvious reasons. The brain, because it's going to destroy your brain. It's enclosed in the skull. With the lungs, you can't breathe. You have fluid accumulating in the lungs. And around the throat, if it starts squeezing off your larynx, you won't be able to breathe. Right? And then the biggest problem here, or another big problem, is that when you trap the water, it doesn't allow biochemical reactions to work properly. So you have to worry about risk of damage to the actual cells themselves. Right? And then finally, just think out of the box. Always look at the possibilities. These first 2 weeks are just dense with information, and you just have to take the time, make your note cards, do everything you have to do to make sure it makes sense to you. If you have questions, make sure you email me with them too.